Okay, hi everyone. All right, picking up where Tool 3 left off, let's move on to Tool 4. Because Tool 4 now is adding all of the different motions of the Earth into consideration to see how our view of the sky moves and changes, not because the stars are moving, not because the sun's moving, but because the Earth is moving. And how is the Earth moving? Well, the Earth is doing three motions, right? The Earth spins once per day, right? So the Earth rotates on its axis once a day. And so since the Earth is rotating this way, that makes the sky look like it's rotating. I'll put it here, in the opposite direction, right? Over one day. So the stars, star A, star B, all of them are going to start in a certain position, go all the way around the rotation axis of the Earth, go all the way around the north and south celestial poles, and come back to their starting position one day later. And also, the Earth is revolving around the sun once per year, right? The Earth starts here, 6 months later it's over here, the next 6 months later, 1 year has passed, the Earth starts back over here, right? And notice that the Earth's axis is always tilted in the same direction, right? It's a common mistake that a lot of people make is that they think that as the Earth revolves around the sun, that's going to change the orientation of the Earth's axis. And it doesn't. Well, at least it doesn't over 1 year, right? The Earth's axis does shift, but we'll get to that on the next page, right? But not over 1 year, right? This is northern winter, right? So in the winter, the Earth's axis is tilted toward Polaris. 3 months later, now the Earth is over here, and the Earth's axis is like this, and the North Pole is still pointing toward Polaris. Now in summer, the Earth's axis is still pointing at Polaris, right? Polaris is the North Star, and the North Pole is angled at Polaris. The North Pole is aligned with Polaris all year long. At least in the modern era, right? So this is what causes stars to be seasonal, right? Some stars are summer constellations, some stars are winter constellations, not because the stars change, but because the Earth is in a different position. Because, of course, whether stars are winter or summer constellations depends on whether you can see those stars during winter or summer at night, right? Because if you're looking for the stars, you're only going to see them at night, right? If the Earth is here, you're going to see these constellations, Taurus, Gemini, Cancer, right? These are the constellations that you can see at night when you're not looking toward the sun, right? These constellations over here, Scorpius, Ophiuchus, Sagittarius, Capricornus, right? These constellations do rise in the winter. They're just up behind the sun. If the Earth is here and the sun is here, then these constellations are behind the sun, and you can't see them because they're up in the daytime and the sun and the blue sky is blocking your view. Right? So that's what makes these winter constellations, is that these are the constellations you can see at night in the winter. When the Earth is over here. And you know that it's winter because what makes it winter? Well, when the northern hemisphere is angled away from the sun, then the sun's going to be lower in the sky, we're going to get less direct sunlight, it's going to be colder, it's winter. When the Earth is here, then the South Pole is angled toward the sun, the southern hemisphere is angled toward the sun, and the sun will be higher in the sky in the southern hemisphere. They'll get more direct sunlight. It'll be hotter. It'll be summer. So we call Taurus, Gemini, Cancer, we call them winter constellations if you live in the northern hemisphere, right? But if you live in the southern hemisphere in December, let's say, right? It's summer in December in the southern hemisphere. And therefore, Taurus, Gemini, Cancer, these would be summer constellations because it's summer for you in Chile, Australia, New Zealand, whatever, the southern hemisphere. Right? 3 months later, now the sun is shining on both hemispheres equally. The sun is shining more straight down on the equator, so it is spring or fall. 3 months later, 6 months have passed. Now the northern hemisphere, the North Pole, is angled toward the sun, so it's northern summer, and the South Pole is angled away from the sun, so it's southern winter. And now if you live in the northern hemisphere, like we do, now these constellations are visible at night, right? Ophiuchus, Sagittarius, Capricornus. These are visible at night when the Earth is when your location on Earth is rotated away from the sun. So these constellations, when the Earth is over here, these constellations are behind the sun, and therefore they're up in the daytime. These constellations are up at night, so you can see them at night in the summer, when the Earth is here in its orbit. All right, so that's what causes the seasons, is the tilt of the Earth, and whether your hemisphere is tilting toward the sun or away from the sun. All right. And then the Earth is doing the third motion, right? The precession. The Earth's axis is wobbling, so actually the Earth's rotation axis is not always the same all the time. It does wobble, but very, very, very slowly, right? It takes 26,000 years for one full wobble. And so, like I said, in the modern era, for the last few hundred years, the North Pole is pointing at Polaris, and therefore Polaris is the North Star. Right? Over the next 12,000 years, the North Pole is going to wobble this way, and so for the next, about 500 or 1,000 years from now, the North Pole will be pointing over here, and it won't line up with Polaris anymore. Polaris will just be another northern star. Right? Polaris will still be there, it just won't be lined up with the North Pole, so Polaris won't be the North Star anymore. Right? In 12,000 years, the North Pole will have wobbled over and be aligned with Vega. So in 12,000 years from now, mark your calendars, in the year 14,000, we will have another North Star, but it'll be Vega. Which will be even easier, because Vega is a lot brighter than Polaris, so people living in the year 14,000 will have an easy time seeing the North Star, because Vega is one of the brighter stars in the sky, and it'll be lined up with true north. That'll be nice and easy to tell what direction you're looking. Hopefully people in the year 14,000, have compasses and whatnot, and they don't need to be told which way is north, but hey, always good to have a backup. Okay. So, what'll happen in the year 14,000, right? What'll happen 12,000 years from now when the stars haven't moved, right? Taurus, Gemini, Cancer, still over here. Ophiuchus, Sagittarius, Capricornus, still over here, right? The sun hasn't moved, the stars haven't moved. It's just that the Earth, instead of the Earth's axis being pointed toward Polaris, it's wobbled over so that now it's pointing at Vega. Which means during this time of the year, when the Earth is over here, the northern hemisphere is tilted toward the sun. If your hemisphere is tilted toward the sun, then it must be summer. And the southern hemisphere is angled away from the sun, so it'll be southern winter. And then 6 months later, now the northern hemisphere is angled away from the sun, so this will be northern winter and southern summer. Which means what happens to the season you can see the constellations? Well, when the Earth is over here, you'll only be able to see these constellations in northern summer. I guess I can write this sideways. Right? So now all of a sudden, in the year 14,000, now Taurus, Gemini, Cancer, they're summer constellations. The stars haven't moved, the sun hasn't moved. The only thing that's happened is that the tilt of the Earth has shifted over, so that from our point of view, here in the northern hemisphere, it'll be summer, and now you can see these constellations at night, when you're facing away from the sun. Okay? And Similarly, right, because now that the Earth has wobbled over here, it's northern winter, and which means that Ophiuchus and Sagittarius will become winter constellations. It happens very slowly, right? The shift in the Earth over thousands and thousands of years will change our view of the stars. Because, of course, whether it's summer or winter doesn't depend on the stars. Whether it's summer or winter depends on the sun, and whether your location on the Earth is tilting toward the sun or away from the sun. Right? So we tell time, we tell dates by the sun. It's going to be summer over here and winter over here in the year 14,000. But the stars in the background will have shifted. So that instead of being up at night in the summer like they are now, Sagittarius will be up at night in the winter. Okay. All right. I mean, this is... If you're doing archaeology, say, right, if you're studying how ancient civilizations did astronomy, which is a fascinating field unto itself, you got to take this into effect, right? The Earth doesn't wobble fast enough to change our view of the stars over the course of 500 years, 1,000 years. Maybe 1,000 years. Well, yeah, 1,000 years. But just over 500 years, things don't change that much. But if you're looking at how civilizations thousands and thousands of years ago did astronomy, you got to take this into consideration. Their view of the stars during different times of year was slightly shifted from the way ours is, and therefore the astrological signs are different and all the things we talked about in the video, right? And so if you're interested in the views of the stars from, ancient Babylon, from ancient Egypt, from the Anasazi in the Americas, ancient China, ancient Africa, right? You got to say, well, the stars haven't changed that much in thousands of years, but the Earth has shifted. And therefore, all of those views will be wobbled a little bit from our point of view. Okay. All right. Let's look at these practice problems. Here we're not taking the wobble into consideration. Now we're just saying, okay, how does our view change over one night? Okay. This is the same diagram we had in the previous tool. Here, we're rotating it a little bit, right? Instead of Polaris being off on the left, Polaris is smack in the middle of our view. So if this is Polaris, then the point on the horizon right underneath Polaris, that must be due north. And if you're facing due north, then if north is into the page, if you're looking into the background, if you're looking into the page and that's due north, then if you're facing north, what direction is to your left? West. What direction is to your right? East. All right? So, and as opposed to here, where if this is Polaris, the point on the horizon right underneath Polaris, that's north. This is east. This is west. This is south, just like we had last time. Right? So basically, to go from here to here, we've taken this view and we've just rotated it. So that instead of north being on the left, north will be into the page. And south will be out of the page. Right? If you were on Earth looking toward the camera, or toward you, the reader, you'd be looking south. All right. So, what direction are you facing in the left diagram? If you're facing into the page, what direction are you facing? You're facing north. How do you know? Because that location is right underneath Polaris. On the left diagram, fill in the boxes with the numbers that correspond to star A's positions. Okay, well, this box right here is what? This box right here is at a low altitude, just a little bit above due north. Which location is that over here? Well, due north, a low altitude, just a little bit above the northern horizon. That's got to be position 3. So this must be position 3. All right. What's the other easy one? How about position 1, right? Position 1 is straight up over your head at the zenith. So which one is that? Well, if you're there, then straight up over your head at the top of the sky, that's got to be position 1. All right, so with 1 and 3 nailed down, now 2 and 4 are the trickier ones. What did we decide last time? If you look at position 2 and position 4, position 2 is above where on the horizon? It's above the northwest. And position 4 is above where on the horizon? That's the northeast. So, position 2 is right above the northwestern horizon. So, if this is north and that's west, then this must be northwest. And right above that, that's that box right there. So this must be 2. And then this must be northeast, which means right above the northeastern horizon, that's position 4. All right. And so on the diagram on the right here, how does star A move? Well, it's moving in numerical order. Position 1, 2, 3, 4, back to 1. So star A is moving like this, 1, 2, 3, 4, 1. On the right diagram, it's got to do the exact same thing if we're looking north. So then star A must be going around Polaris this way. What direction is this? If you're going 1, 2, 3, 4, back to 1, is this clockwise or counterclockwise? It's counterclockwise, right? Because the Earth only goes in one direction, right? The Earth is only rotating eastward. And since the Earth is rotating eastward, then when you're looking north, then all of these northern stars are going around Polaris the other direction, counterclockwise. The point directly overhead is called the zenith. What numbered position is that? Well, the zenith is position 1, right? Star A at position 1, straight up over your head. Suppose star A is at position 3 at 6 p.m. Okay. When will it be at all the other positions? In both diagrams. So, position 3, 6 p.m. Okay. Okay, so if we start at position 3 at 6 p.m., star A is going to go all the way around and come back to position 3 in how much time? How much time does it take the star to go around the pole one time? Well, is the star really moving? No, it's the Earth that's rotating, right? The Earth is rotating on its axis, and therefore this star looks like it's spinning around the North Celestial Pole. How much time does it take the Earth to rotate once? A day. So how much time does it take this star to go around the pole one time? A day, right? 24 hours. So if it takes star A 24 hours to go all the way around once, right? 24 hours to make a full circle. How much time is it going to take to make a quarter of a circle? Well, it's going to take a quarter of a day. So to go through each quarter of the circle, it's going to take 6 hours, 6 hours, 6 hours, 6 hours. A full 24 hours have passed. So if we start here at 6 p.m., all of these stars go counterclockwise. So it's going to go from position 3 to position 4. What time does it reach position 4? 6 hours later. All right, what's 6 hours after 6 p.m.? 6 hours after 6 p.m. is midnight. And then it's going to take another 6 hours to reach position 1. So then it reaches position 1 at 6 a.m. And then 6 hours later, it reaches position 2 at noon. And then 6 hours later, it comes back. 1 full day has passed. It's back at position 3. It's 6 p.m. the next day. So if we're going to do this for the diagram on the right, then our answer should be the same, right? It's going to reach position 1 at 6 a.m., position 2 at, what's the best place to write this? I'll write this over here, right? So position 2 at noon, and position 4 at midnight. All right. not the cleanest diagram. Hopefully you drew everything more tidy and easier to read, but I wanted to draw all those extra annotations for you. Okay. So I left off last time saying, if you know where a star is, if you know the position of a star, then you know where it's going to move next. Well, this is exactly what we're talking about, right? If you know that the star is at the zenith, if the star starts out at the zenith, then you know where's it going to move next. It's going to move down into the left, into the northwestern sky. And then it's going to move, if it's at position 2, now it's going to move down into the right to be low in the northern sky, and then up into the right to the northeastern sky, and then up into the left to go directly overhead. If you know where a star is, you know where it's going to move next. So the altitude and the azimuth tells you more than just position. It allows you to predict how you should track the star. It allows you to predict how you should move your telescope. If you wanted to watch star A all night long, that's a problem, right? You can't just point your telescope at a star and leave it all night, because the star is going to move, and it's going to move out of the field of view of your telescope. So if you're tracking a star over long periods of time, you got to move your telescope to move with the star. And how do we know how the star is going to move? Well, if we know its position, then we know all we need to know. Because where the star is right now will determine how it moves minute after minute, hour after hour next. So all you got to do is set up your telescope, move your telescope the same way the star moves, and you can watch the same object, the same star, galaxy, planet, what have you. You can watch it all night long. Which is pretty slick. It's a nice way to solve a lot of problems. Okay. All right. One more thing to do, and that is, so far we've been talking about the positions of stars in altitude and azimuth. Let's talk about right ascension and declination, and that's what we get into in Tool 5. So, hopefully this all makes sense. If you've got questions about Tool 4, just come into office hours, post a question to discussion boards. And if this is all good and making sense, then go ahead and tackle the practice and then move on to Tool 5. And after you've done Tool 5, then I'll meet you back at the review video for Tool 5. All right. Good luck, and I'll see you there.